Okay, here we go. We start the tech talk about wide bandgap device. Fall is approaching soon, and Indian summer in the Northern Hemisphere will show also up. And then, consequently, Thanksgiving is coming, especially in America. We will say in Germany, Erntedankfest. The last articles from my magazine are the subjects where we built on the platform for this discussion. And I welcome the people in the roundtable, which is Peter Friedrich, at this time the ECPE chairman, and David Levett from Infineon, and Laurent Martinez from CALY Technology. So we can start with the first question from the auditorium. Here we have, compared to a traditional GDT plus resistor plus TVS surge PI filter, what added value brings CALY's SiC CLD use?
Yeah, so this is Dominique Tournier from CALY Technology. So a current limiting device, CLD, is a device that is clamping the current. It's, let's say, a dual to a TVS. So this is a serial protection device that is in principle implemented in a P configuration for protection for a power line or a data line. You are generally putting in parallel with the line a TVS that is clamping the voltage when you have an over voltage in an electrical equipment. Implementing the CLD will permit to reduce the energy dissipation in a TVS. That means that you will have a more compact system, faster, a simplified design. As an example, if you go for a classical implementation of protection with a resistor and TVSs and a GDT, you will end up with a footprint of 8.8 square centimeter. If you replace the power resistor by a very small, tiny CLD, you can shrink down the size of the TVS, and the total footprint of the protection will be divided by more than 50%. So it will have a PCB area shrink down to 3 square centimeter. So you will have a very small protection implementation, saving PCB surface, and that gives the possibility to save weight, for example, in an airplane, on a calculator, to have a very reduced footprint of the protection impact on the system.
Thank you, Dominique. For paralleling IGBT, the gate threshold voltage seems to be more of an issue than for SiC MOSFETs. Can you help explain why that is?
Peter, would you like to take that question, please?
Well, I can try my very best to do that. Yeah, so based on our investigations, the major difference is due to the difference in the transconductance. So silicon devices like IGBTs or even CoolMOS devices have a very steep transconductance, what means if you have a small deviation in the VTH between two parallel parts, it might happen that one is already fully on, the other one is off, and then of course it might lead to some oscillations and problems. So in silicon carbide MOSFETs, well, it's still a weakness of silicon carbide MOSFET that the transconductance is much lower than in silicon, but it helps in paralleling because a similar deviation in the threshold voltage between different silicon carbide MOSFETs will not have such a big difference in the conductivity behavior of two parallel MOSFETs. And for that reason, threshold voltage variations, at least if they are in the same range as we know it from silicon, are of less importance for paralleling SiC MOSFETs. Anything you want to add, David, from your experience?
Yes, no, I think you've explained it. So what we're saying is, I think if there's a slight difference in the gate threshold, one device might turn on slightly earlier than the second device with the same gate voltage, but that won't result in a very large difference in current as it would with an IGBT. I think that's what you're saying.
Thank you for this explanation. And we're ready to go to the next question from the audience.
Yeah, what electrical research standard CALY's current limiting devices was designed for? The CLDs have been initially designed for aircraft lighting protection. So they should be compliant with the TO 160 section 22, so the aeronautic standards, to meet various waveform. The most aggressive, let's say, is W5 level 5. For those who know, it's a B exponential pulse, 1.5 kilovolt, 1.5 kilo amp. And to address those waveforms, indirect effect of lighting in equipments, usually bulky TVSs are implemented in the protection cards. So the CLD benefits is to reduce the footprint and induced power in TVSs. The waveforms are those kind of waveforms, very aggressive. In principle and domestic application, we are more considering the W2. It's a bit exponential waveform, maybe known more as 820 waveform, 8 microsecond increase of voltage, 20 microsecond decrease, will be exponential with lower level of current injected in the equipments. So initially they were designed for this, and the CLD have been designed to sustain 100 pulses repetitive without any degradation of their characteristics.
Thank you, Dominique. And we're ready for the next question from the audience. The question is there any advantage of a trench-based design over a planar design for paralleling SiC MOSFETs?
Peter, I'm expecting you to help, please, with this.
Okay, David.
Yeah, sure, it will be my pleasure. Yeah, we do think that even if we just stated that threshold voltage variations are of less importance compared to silicon, but of course still the spread between different VTH values should not be too big. And here's an essential advantage of an trench-based part compared to a planar MOSFET, since in a planar MOSFET control of the threshold voltage is by far not as easy as in a trench-based device. Also in a trench-based device, you can very nicely define the doping concentration in the base layer, which is more or less a key parameter for the threshold voltage, and you can keep it also very stable across the whole population of devices across the wafer, or also from run to run. While in a planar device, you are always limited by some mask variations, which might also lead to a larger threshold voltage variation. Another thing which is still a matter of fact in case of silicon carbide MOSFETs, if you look to the planar devices, they usually have a lower temperature coefficient, what might be good for, let's say, losses at higher temperatures, but for paralleling, it means that usually you have a certain, let's say, range where you have a certain negative decay. in planar parts, which is in a trench-based MOSFET due to the significantly higher positive TK more or less ruled out. So these are the two aspects which I believe are a certain advantage for planar versus trench-based devices versus planar devices. However, as always, with let's say certain refinements in structure and processing, you can balance it out. So I wouldn't say that this is a fundamental key difference, but it is easier to manage those things in a trench-based device.
Thank you, Peter. Let me ask just something in between. Peter, you had the ECPE event. Do you have some highlights to share with us from the ECPE wide bandgap events that would be of interest to our audience?
Well, first of all, it was the first event after more than 1 year where we met in person. So I can only say that was, besides a technical discussion, significant highlight, I think, for everybody being on site there. First time talking to each other, let's say having more exchange than being ever possible via a virtual event. So that was, I think, one of the biggest highlights, and it worked out very well also in the hybrid configuration. So as I said, besides the technical topic, that was really a very nice experience being somehow back to the normal times. Yeah, regarding the technical presentations, we had the typical wide scope of the gallium nitride and silicon carbide topics in the ECPE user forum. So starting from some device discussions up to applications, reliability was one of the key topics, as always, deep discussions about that. There was a very good presentation from the AQG 324 team regarding reliability aspects for automotive power modules. So that was very, very nice insight into the differences between silicon and silicon carbide and how to address it. So what kind of proposed test methods we should look into. So it's still a work in progress, but the team is really working very hard there to develop something what automotive user or customers can use for qualifying wide bandgap devices. So that was really very impressive.
Thank you, Peter.
Yeah, you're welcome.
So let my people get the next question in, and always question about the yields for SiC and what kind of actions have been addressed to solve this problem.
Peter, do you want to take? I think Peter is an expert here, perhaps.
David.
Thank you, Peter.
Yeah, sure. So, yeah, it's a matter of fact, still we have to deal with the situation that silicon carbide defect densities are higher than in the well-established silicon technology. Yeah, what kind of actions have been addressed here to solve the problem? Good question. First of all, one need to understand what kind of defects are the ones which are really what we call killer defects, and what kind of defects we might be able to live with. And here we made very good progress over the last years, understanding the defect household and how to, let's say, look for particular defect structures which we need to eliminate, while we can maybe accept a higher level of defects which are not critical. So one example here, if we look to the so-called mesoplane dislocations, which are responsible for the drift of bipolar devices like the body diode of MOSFETs or high voltage PN diodes. So here, tremendous progress has been achieved on both on the material side by dropping down the starting defect density with respect to this particular defect, but also very important, there are measures now in place how we can transform the remaining defects during epitaxial growth into something which is less critical. So these are the major ways how to tackle the higher defect density in silicon carbide. Of course, we see continuous improvement from the material side. We need to make sure that once we step into the next diameter, so people talk about 200 millimeter on silicon carbide right now, that we don't go a too big step back in defect density, but otherwise we would say that meanwhile the defect density level in silicon carbide is, I would say, manageable. Still not where silicon is, but with the understanding we have right now, we can deal with it.
Thank you, Peter. My understanding of SiC is that you have a much higher current density. That means the die sizes are smaller, and that may allow to get more good die from the wafer. So
that's true. That's true for, let's say, a comparable defect density. However, the defect density level between silicon and silicon carbide, it's still orders of magnitude difference.
Yeah.
While the die size is maybe, let's say, 1/5 of the silicon. So still there's a mismatch, I would say. So it does not compensate for the defect density related yield loss.
Okay, Peter. So we can jump to the next question regarding oxide charges, DIT, NOx, and M that might shift V threshold. Is there an advantage using SiC instead silicon?
There's nobody else who would like to answer this one. I can try once more.
You are definitely the expert.
I may a few words, and you can complete and add, Peter. Well, there are significant improvements, as just commented before, on the threshold stability, and the devices are tested now with standard and qualified regarding automotive requirements. So devices that are on the market are stable with respect to the application parameters variations. And the benefits versus silicon is the benefits in terms of operating frequencies, power losses, compactness of the inverters. There are still some improvement to make to have a more reliable product, but devices that are on the market are qualified product. This is the point of view. Maybe Peter, you can comment and surely add more information.
Yeah, you're absolutely right, Dominique. We have a physical difference, and this is the bandgap itself, which especially for the oxide also means that there are potentially much more defects in the forbidden bandgap, which can contribute to VTH instabilities. So therefore, yes, there's a lot of progress, but that there's an advantage of using SiC compared to silicon regarding VTH drift, I wouldn't like to confirm this. It's rather the other way around. You have more challenges in SiC.
Thank you, Peter. Here we go for the next. So that question is about cooling and thermal requirements evolving as SiC becomes more mainstream.
So perhaps I'll start with that, and then people can add to it.
Okay.
So one of the reasons we use silicon carbide is because its losses are less than silicon. But to counter that, silicon carbide is expensive. So we want to push every single electron through that silicon carbide. We want as many amps per dollar or amps per euro we can get through that silicon carbide part. And the chips are smaller, so it's harder to get the heat out of the chips. So to me, cooling becomes a bigger issue, because we can put more chips, more current rating in the same size package. And so it becomes more of an issue to get the heat out. Now, I think one kind of advantage is that silicon carbide is more expensive. So I can afford, we can pay more for the cooling system or more for the module design. So for example, we might say we can use aluminum nitride ceramics instead of aluminum oxide to get the heat out better. We can use heat sink technology with embedded heat pipes rather than just aluminum extrusions to get the heat and spread it away from the module. So I think we can balance that. We can spend a lot more on the silicon carbide, but then to get the higher current out of that same silicon carbide, we can afford to have a more complicated, more expensive thermal solution. As I said, using heat pipes, copper, advanced bonded fin, things like that. So please add, anyone else can add.
Thank you, David.
And I'll add one more point is, in general, silicon carbide is not as good as silicon in terms of power cycling. So keeping the parts cooler and reducing the delta T's during overloads or extreme conditions becomes more critical. So in this case, cooling is more important. The thermal requirements are more important than with silicon.
Thank you for that explanation. We are ready for the next.
So how to implement CLDs to sustain positive or negative surge waveform. When an equipment is subject to a strike lightning, we can have either positive or negative waveforms, and this is not possible to predict the way it will be aggressing the equipment. So there are several possibilities to solve this issue. One is if we have unipolar protection to implement is only to implement one die, or to have bidirectional current limiting device connecting two devices head to tail. This can be made using two spare die or using bidirectional devices with two die embedded in the system. And to evaluate how to implement this in the topology of the system, we have developed a LT-SPICE model that makes possible to simulate the aggregation, to check if a positive or negative waveform is well protected, if there is a need to implement diverting energy to the ears or not, in fact. So two flavor devices can be used, unidirectional or bidirectional. And as we're dealing with surge, we often end up with blowing and explosion in test lab. This is why this kind of simulator can be useful also too. So yeah, it depends, let's say, also of the impedance of the system. Sometimes you have some filters, some heavy load with capacitors that also are acting as filtering. So the impact of positive or negative surge needs to be evaluated before selecting the proper implementation of the prediction for negative or positive waveforms.
Thank you, Dominique. For a Monte Carlo analysis, you have selected RDS on and switching losses as parameters. Why these and not other parameters? That's addressed to David and Andre at Infineon.
Okay, well, David, I'll try and take this. Oh, this is, yeah, not a simple question, perhaps. So we ran the Monte Carlo analysis for paralleling parts to say if you randomly select 4 or 3 or 6 parts in parallel, what is predicted sharing? Now, our key design criteria for this analysis was junction temperature. We wanted to see how the junction temperature would spread. We weren't specifically looking at current sharing, for example, how do current sharing vary with gate threshold, as we've talked about, or layout changes. We simply wanted to say, assuming that the parts all turned on at the same time and we're in a reasonably symmetrical layout, what would the current sharing be and what would the junction temperatures be? So for that, the two key parameters that affect temperature are the RDS on, which affects the current and the current sharing, and then the switching losses. So that's why we selected those two and ran the Monte Carlo analysis, and then we could get a spread of temperature. So then if we see a spread of temperature of 10 degrees plus or minus 5, that helps us design the margin for the final design under worst case conditions. I hope that answers the question.
Thank you, David. What do you think is the practical limit for number of these style of modules then can be paralleled? That's
okay,
awesome.
David. Perhaps I'll try and I'll start with this. Again, I think this is a pretty common question that people ask, and we're talking about PCB-based modules here, and how many you could parallel, because people are saying, "Hey, could I parallel 20 or 30?" And there must be some practical limit. When you try and parallel parts, I think there's two ways you can do it. I'll wave my arms around a bit here. So one way you can put modules side by side in a line, and then this means you can have a symmetrical layout to the capacitors, but the output of the devices, it's harder to make the path equal. So that's one limitation. Another option is you can put devices in like a circle or a pentagon, and then again, you can make the outputs obviously very symmetrical because they can all go to a center point, but the outer ring can also be more complicated. My gut feel is 5 or 6 is probably the limit you're going to get to. Any more than that, and getting symmetrical layout, symmetrical gate driver, and then the difference module to module becomes problematic, and you just end up derating so much that you lose the advantage of just adding more modules. So my gut feel would be 5 or 6 would be a limit. But please, if you can do more, I'd love to see the design. That would be a beautiful design if you can do more. I think that's smart. If anyone else wants to add to that, please.
Thank you, David. Where do you think is the upper power limit for PCB-based power converter design?
So I'm sorry, I'm talking a lot here. Perhaps
David,
that's all right,
Peter.
I'll take that one, Peter, if that's all right. I think we see more and more in industry a trend towards going to PCB-based designs rather than the traditional bus bar and screw designs that we've had in the past. I think this is for a couple of reasons. One is with silicon carbide, using a PCB, we can make lower inductance. We can have multiple pins in an easy module, for example. We can use the PCB as a multi-layered laminated bus, keep inductance loops very low. And so we could see, for example, if you take a PCB-based module and a screw-type traditional module, you can get half the inductance with the PCB-based. I think another reason is that in terms of assembly and test, having a PCB-based design is more reliable and simpler in high volume than having, screwing pieces together and using bus bars. So we're seeing this trend, I think, higher and higher and higher. People are going, we want 50 kilowatts, 75 kilowatts, 100 kilowatts. Now, I think there's some limitations. You can go to heavy copper boards. You can start saying, I'm going to have 6 layers of 4-ounce copper, which gets expensive. You then have, that forces you really to flip to press fit technology rather than soldering. And then you can add power jumpers and add copper bars on the board to help carry current. But I think, it's, the limitation is losses. So I squared R, you go from 100 to 200 amps on a board, you increase the losses by a factor of 4. So I'd say 100 to 150 amps is possible. You start going 200 and 250 amps, it becomes problematic. So I think the limit at the present is in that kind of order of magnitude in terms of current. And please, if anyone else wants to add to that, I'd be open.
Thank you, David. Let me see if my backstage has any more questions ready for us. There is a question coming. With the gate driver design shown, how would a Miller clamp be implemented? It's again to David and Andre.
Okay, well, thank you. I'll try this one. This actually is a very popular, I say common question again that we have. So if you use a single gate driver to drive multiple parallel devices, you have to somehow separate or put impedance in the auxiliary source. Otherwise, we always joke, we call them teenager electrons because they go where we don't want them to go. They will flow through the auxiliary source rather than the power source. And this is not a good thing. So I think if you look in our article, you can use common mode chokes, or you can use some impedance and a separate boost stage to sort of, I can say, quasi-isolate the sources of different modules to prevent this circulating current. However, if you do that, then I think it makes it very, very difficult to implement a Miller clamp, because if you put a Miller clamp from a gate driver, then you're reconnecting all those sources to a common point. So I'll be honest, I don't know of a simple way of implementing a Miller clamp in a system where you have multiple devices in parallel. I think it's very, very difficult. And again, if anyone's got a great way of doing it, please tell me, because I'd love to know. So I think that is a real, real challenge. And so perhaps you just have to, I mean, you just have to not use a Miller clamp and use a higher negative gate voltage and perhaps a small capacitor gate to source to prevent the problems of Miller. And if anyone wants to add, I'm open to all any more comments on that.
Thank you, David. I like your explanation of teenager electrons.
Oh.
I have to keep that in mind.
Yeah, well,
That's great.
I've had two of them, and I still got one teenager. So
Okay.
sometimes they do the opposite of what I ask them to do. I'm not sure, but they just do that. So
Yeah, gentlemen, there is another question. SiC devices, pro and cons for SMD devices versus THT.
Bodo, if you don't mind, I can try this one.
Friedrich, thank you.
Yeah, what is the advantage of through-hole packages? So I think THT means through-hole technology.
Yeah.
So our classical pin type discrete packages. Usually those come along with very good thermal performance, which is in case of silicon carbide, of course, a big advantage due to the discussion we had before with the higher power density levels, etc. On the other hand, typically they have pretty high strain ductance, what limits the speed options. SMD, on the other hand, of course, has the opportunity to get down with the strain ductance to very low levels. And of course, the assembly advantage is also obvious. So this automated assembly compared to a through-hole device, where often even a manual attachment of an heatsink is required. So these are big differences. I would say, at least what we try is to combine some of those goodies into new package types where it is possible to have the good thermal performance of a through-hole device and the advantage of the SMD. If you can achieve something like that, then you are on a very good way to squeeze out the best out of SSC. So this quadruple DPAC and double DPAC with topside cooling options, which we launched recently. So this is already one example what is possible, because here we get really the same RTH compared to a through-hole device, but all the advantages of an SMD type. So therefore, if the combination would work best, the combination of the thermal performance from through-hole with the electrical and assembly performance of an SMD.
Thank you, Peter.
Just a comment on this and additional information concerning protection devices, for example, for the CLD, as the fault are very short, tenths of microseconds, in fact, all remain in the die. So definitively the SMD devices implementation is more suitable for protection devices because we can reduce the footprint. And we do not need to have a very high dissipation capabilities.
Thank you, Dominique. I'm sure I see a question coming up. That's about paralleling and about separate gate driver circuits rather than a single common driver.
Okay, perhaps I'll take that one. But up first, wait a sec, I've got my. Can I just show Peter was talking about this part, and I'm going to try and show it on my camera. If I can show it here, you can see. So this is what Peter's talking about. So this is a surface mount device, but it has, you can see top side cooling. So it's like a TO247, but surface mount. You have the similar area. And this, as Peter said, combines the advantages of surface mount with the cooling performance of a TO247. So I just want to show. So this is the new Q packages Infineon and other people are coming out with, which I think are an advantage. Okay, the question is, so again, I think this is a common question. People say, well, if I want to parallel some silicon carbide MOSFETs, I have 3 devices, I just use 3 gate drivers. It makes life simple. And yes, to some extent it does. I don't have to worry about this, my teenager electrons, because my 3 gate drivers are totally isolated. However, then you have to control 2 parameters really well on your gate driver. One is the timing. Obviously, I need to turn all 3 devices on at the same time. And if I'm using a driver IC that has a 100 or 200 nanosecond difference part to part and over temperature, then that's not going to work. And then the second thing you need to control is the gate supply voltage. If you're turning one on at 15.5 volts and one on at 16 volts, again, dynamically and statically, they won't share. So it is possible to use separate gate drivers. You just have to make the design very carefully in terms of the timing and the supply voltage. And then, another disadvantage is you're just going to have more components, and more components typically means less reliability. So we would say if you can do it with 1 driver and drive 3 devices at the same time, which I think we've shown is very possible, this is the preferred solution. But you can take that alternative route if you want to do that.
Thank you, David. And I remember in my early days learning my profession in the test lab. That time, I remember that if the switching times and the overlap is not real correct, you have the risk of shot through and can damage a lot of devices by that.
Yeah, you're exactly right. And so that's why, because we want to minimize the dead time or the delay, interlock delay time between 2 devices with silicon carbide, we want to reduce that as much as possible. Then timing on the gate driver becomes really, really important. Otherwise, as you said, we get a shoot through and boom, we have a failed device.
So that's about heat dissipation.
I can try this one. So if you have a traditional D package device, whether it's a MOSFET or a silicon carbide or an IGBT, it's soldered to the board. The heat then comes into the board. I need to get that heat away. Now, to me, there's a couple of methods that you can use. One is, typically people will put a lot of power vias, I call them power vias, that you can even fill with solder around the device, run the device to get the heat to the back side. And then somehow you can either heat sink that, you can use a thermal pad, and a heat sink to get the heat out of the device. A second method is to use IMS, that's isolated metal substrate, which is very, again, common for surface mounting parts. And then this gives you the isolation and also helps remove the heat from the device. But it is difficult. You have multiple devices, a lot of heat concentration. There are limits on board temperature, perhaps typically only 105 degrees C. And so it can be very difficult to keep the board within its temperature and the devices within their temperature and get that heat out. So it is a real challenge. And it is something that's quite difficult to model. Thermally modeling a heat sink with a fan is relatively simple. Trying to model the heat dissipation with convection cooling on a board is the engineers that do it tell me it's difficult, and I believe them. So not an easy solution, not an easy problem to solve. And again, that's why we're seeing the people developing these topside cool devices that I showed you earlier. So again, anyone else would like to add to that?
Thank you, David. The question is, if IMS for high voltage devices, 1200 volt, is that reliable?
I mean, if no one else wants, I'll try. So to me, there's no fundamental reason that IMS can't be reliable. It's just a question of the insulation system of design. So I can't answer that. That's something you would have to talk to the supplier of the IMS material. But I don't know that there's any theoretical reason why you can't make an IMS have a higher voltage isolation capability. But again, that's something that the supplier would have to show test data and reliability data to show that that would work.
Main issue is maybe if people are changing the operating temperature, that can be more constraining to find a insulated material if they want to operate at high temperature.
Yes, yes. The higher the temperature, the more challenging it is to get the isolation material. Agreed. Good point.
Thank you, Dominique and David. Which packaging is more suitable for automotive applications? Is TO easier to qualify?
Yes, please, sorry.
Dominique, go ahead.
Yeah, I will say very simply as an engineer, the less interface material, the easier to implement qualification because there are less cycling, less mismatch of material. So maybe that makes more simple, even if we have also less power. But I'm not a power module expert, so feel free to give more details.
Yeah, from my background, and that's 2.5 decades ago, but packaging has not changed too much. At that point, if you have TO devices, the biggest TO device you have is TO3, plastic, and you can spread them out over a big heat sink, and you have the concentration of heat spread out over a bigger surface. That's the only big advantage I see, and TO packages are good qualified in automotive processes as far as I know.
Perhaps Peter knows more than me, but I think Peter mentioned earlier that I think that the standard 324 is used for modules. And then I've seen that for TO247, they use the AQ101. So I'm not sure, but once you have a standard and you have to test to it, I don't think it matters what the package is. You still have to run the high temperature reverse bias and the thermal shock test and the humidity. You have to do those same tests irrespective of the package. I'm just saying, I think that some of the smaller plastic packages might have a different standard. Peter, would you want to comment on that?
Yeah, good point. I would agree what you said, David, that once you have a good understanding what kind of things can happen in a particular package platform, you can address it by a proper qualification. So that's, I think, how also in the industrial world the modules enter applications which, by the way, have much more stress and demands towards power electronics packages than in a car. If you take just a module in a train running for 30 years, sometimes 24 hours a day, that's something completely different compared to an automotive application, just regarding the, let's say, stress you put onto the part. So that also shows that with the right qualification measures, in the end, it doesn't matter whether it's a package, a plastic package, or a module. But the efforts to guarantee a high level of robustness and reliability in a module, as Dominique mentioned, there's much more interfaces around, much more materials involved, are in the end, of course, higher compared to a TO. But taking the question literally, whether it's easier to qualify a TO package, I wouldn't say. Once you understand everything around, it's not easier or more difficult.
Thank you, Peter. In case of a DSC, the heat dissipation is 50% of the top and 50% to the bottom, or the asymmetry plays a fundamental role.
So if you want, I'll try and start with this. So if you've got they're assuming about double side cooled modules. Now, if you look at Infineon double side cooled modules, you're right, it's not exactly 50-50, because if you look at the construction internally, you have the chip, there's slightly different connection to the top side to the bottom side, just because of the connection technology. So from memory, it might be 55-45, something like that. There's a slight asymmetry, but it is reasonably close to 50%. And then obviously that depends on the heat sinking. Typically they sandwich them between two plates with a similar performance, and then you have a similar, the grease and the thermal impedance is the same. So you do get a pretty close to 50-50 out the top and bottom, but it's not exactly. The thermal resistance is slightly different, both sides. And then if you have a different heat sink top to bottom, again, that clearly makes a difference. I hope that answers the question. Anyone else wants to add?
Maybe I have a question. What is the benefits in terms of junction temperature reduction with this double side cooling with respect to classical cooling in backside?
Well, in theory, I can halve the thermal resistance. I mean, if I think of it, I've got two resistors in parallel. If I've got 0.1 degrees C per watt from the top and 0.1 degrees C per watt at the bottom, I get 0.05 total for the chip. So you can significantly reduce the thermal resistance. And you see with thyristors or puck style or press pack IGBTs, this is very, very common technology.
Thank you, David.
It's a good question. Good question. If you want more details, you could either look at the Infineon data sheet. I think it might say it in the Infineon data sheet. If not, you can ask Infineon and we'll tell you what the...
Okay, the last question before we come to an end. Why manufacturers do not want to publish short circuit capability of SiC MOSFET devices in their data sheets?
Bodo, if you don't mind, I will try to answer that.
Peter,
so
go ahead.
First of all, it's not fully true in this, let's say, black and white statement.
Yeah.
There are silicon carbide MOSFETs on the market with short circuit specifications in the datasheet. However, it's not so many of them. The reason behind this, to get short circuit capability into a silicon carbide MOSFET has a dramatic impact on the performance. So if you want to achieve something like in an IGBT, you would lose a lot of the RON performance. So that's one reason, of course. So nobody would like to offer something to the customer which is degrading the performance. The second aspect is simply that many of the today's target applications or the major applications where silicon carbide MOSFETs are used right now simply do not require short circuit robustness. Therefore, you can easily live without specifying it, what then also means you don't have to take into account any performance limitations out of short circuit ruggedness. So that's basically, I would say, the major reason for the situation as we have it today. How it will look like in the future when we try to address other applications requiring short circuit capability. So this is currently a big discussion. By the way, not only for silicon carbide, also in the silicon world, in the IGBT world, discussions about short circuit requirements and what kind of times we need are ongoing, whether you can manage it with external circuitries instead of putting it into the device and degrading its performance. So that is a very, let's say, dynamic process right now. But the major reason for not having short circuit in the datasheet right now is on the one hand side, performance limitations, which you need to accept if you do so. And on the other side, some simply application aspects saying, I don't need short circuit, so why then specifying it? Because if you specify it in the datasheet, you are also forced to test for it.
Okay, Peter. So I had come to an end. I'm not quite sure. The talk is over. I thank you to the auditorium and to the speakers. I want to add a short message that we will have this continued on a quarterly base, and our highlight this year will be at the end of November, early December, a virtually event on wide bandgap, which we now continue the 5th year. We had it last year virtually, and we have decided to do the wide bandgap event virtually again in the end in a slightly modified form, and you're all invited to be part of it. Thank you very much, and enjoy the rest of the day. And Peter, enjoy the rest of your vacation. So far, bye-bye, gentlemen.
Thank you.